Okay, hello everybody. Let me start with introducing myself. So my name is Dr. Mendel, and I'm a member of the steering committee here at the Quantum Center at the Tel Aviv University. On my daily job, I'm a head of cryptography and cybersecurity at State Street, based in London. And later, if you have questions, then we have a break so we can discuss this in more details, and we're going to explore to you also more about the quantum activities that we are doing here at the Tel Aviv University. Let me start with please inviting our really honored panelists for the academic panel. So the first, I would like to invite Professor Yaron, Professor of Physics, Director of the Center for Quantum Science and Technology here at the Tel Aviv University. Professor Yakir Aharonov, Professor, Chapman University. Professor Artur Ekert, Distinguished Professor, National University of Singapore. And Professor Vaidman, Emeritus Professor in the School of Physics and Astronomy from the Tel Aviv University. Normally the professors are asking you questions. Today we will ask them questions. Let's see how tough they are and answering. So, yeah. The first question that we would like to ask you is, quantum mechanics is considered to be a very fuzzing theory. What is the most important part of the theory of quantum mechanics that are still missing? And what is your opinion, the route to follow in order to gain better understanding of this missing part? So this is a question to the panel, and let's see them answer.
Yakir, you should be the first one.
No.
Okay.
Yes, so the question is, what is the most puzzling aspect of quantum mechanics, you think? What should be the route to go in order to answer?
I believe the most puzzling property of quantum systems is the fact that, for example, an electron can be at the same time at two different locations. The electron, after all, has a charge and a mass, and when we say that it's at two different locations, what happens to its charge and mass? Is it divided between the two, or is it still at one of them and we don't know where? The usual claim why it must be in two different locations is that there is supposed to be no way to understand the interference property. If an electron goes through two slits, we know that later there will be some point the electron will be never found there, even though it will be there if only one of the slits is open. So therefore everybody says, although we can never see it directly, indirectly we are sure the electron must have gone through the two slits. The answer to this is the fact that, in fact, in quantum mechanics, there are properties that have non-local equations of motion. And therefore, the particle can go through one slit and knows whether the other slit is open or not by the fact that the Heisenberg equations of motion are non-local.
Artur?
Actually, I don't have a good answer to your question, to be honest. Quantum physics is not something that is very intuitive when we sort of start learning about it. So we learn it through mathematics and equations, and it's still very paradoxical. So I find particularly the emergence of inherent randomness, for example, something that is very puzzling, even though if you look at it from the Everett perspective, for example, maybe not, but then it's very puzzling that we live in the universe that is much richer than we think it is. So even though you may say at the mathematical level, we get such a long mileage out of linear algebra, right? But all kind of conceptual consequences are far from trivial. So on a daily basis, you come with a colleague who comes up with yet another paradoxical aspects of quantum physics, and you say, gee, it's ingenious, why haven't I thought about this, and why is it still challenging your intuition? So I think it's full of surprises. It's probably going to be refuted at some point, and maybe we'll have a better understanding, but so far it's just, it's a beautiful intellectual challenge. It works.
Maybe my answer will be kind of strange, because I think quantum mechanics is clear and it's the last word, I hope. And from my point of view, there will be nothing revolutionary new. And I'm happy that here Artur is in the same side, because the only way to understand it is to accept Everett interpretation. Otherwise, I really will be on the position that quantum mechanics is not the final word. But Everett says that yes, electron goes here and here. Moreover, then we can be in two places or in many places in parallel. Everything going according to simple linear equations. Everything is essentially local in a sense there is no action at a distance. We have a very beautiful theory which till now everything which we can calculate and measure agree. So I see no reason whatsoever to believe that there will be some change in quantum mechanics.
Well, maybe I should disagree with Lev. I think that actually coming from high energy physics, we understand very small part of physics, and I think if we will include gravity in the field, as a quantum field, I think something totally different will come out. So that's why I don't think that everything is closed, we understand everything and it works.
Okay, so this is always very interesting when we have a panelist of academia around this, and this is why it's so fascinating. But in that spirit of surprises, I'd like to ask you, please, do you expect more surprises in the quantum mechanics? And which type of experiments are likely to discover such surprises?
Well, we find all the time new quantum effects, and the only way not to be surprised by them is to have the right story to tell about quantum mechanics. You know, if we have a theory of the world like quantum mechanics, it's not important just to have the physical formula or the physical equation. We must have some way to interpret it, to think about it in a language that is free of mathematics. Only if we have this kind of language, we can then think and find what are the interesting questions to ask the theory. If we don't have this language, then mathematics doesn't tell us what are interesting questions to ask. In my research, I found that when I thought about quantum mechanics in the right way, then many, many new sort of called surprises happened, but to me they were not surprises because I had the right language to think about quantum mechanics. And I expect to have more effects of this kind to be found in the near future.
When it comes to experimental refutation, so let me just let me connect it a little bit with the topic of this conference. So when I'm asked by usually journalists about quantum computing and when quantum computers will be built, and then my answer is that usually I would like the whole program of building quantum computer fail for a good reason. And by failure, I mean that building quantum computer, to me, is constructing the most sophisticated quantum experiment that we ever envisage, right? So it's much more probably complex. Building a quantum computer is probably much more complex than an Apollo program, with a number of components, a number of logical qubits that you want to control. So if there is any discrepancy between the prediction and the experimental data, I think it's going to happen in that kind of experiment. So for me, looking from the physicist's perspective, building a quantum computer is constructing an immensely complicated quantum experiment. If things go wrong, if we are able to predict that things go differently, that's another story, of course, then in this kind of experiment, most likely we'll see the difference. So I'm very much in favor of building a quantum computer, but for a completely different reason. I think it will be just wonderful, fundamental experiment challenging our ability of our predictive power in this case. And if it goes wrong, if it just shows that quantum theory is not the last word, that would be great. It may or may not happen, but if it happens, that's the most beautiful thing that the physicist is hoping for, right? So I'm thinking, let's use all this industrial money for the best fundamental experiment. Let people on the commercial side think that they are just after a quantum device, but we physicists are probably about the refutation of quantum physics.
You're recorded, right?
Okay.
Yes, this session is recorded and also transmitted.
That's right.
It's really online now.
Just to reply, I agree that quantum gravity we don't understand, and everything should be quantum, and gravity currently is not quantum. So we need something to add to quantum theory, but essentially I agree with Artur that quantum computer needs that quantum mechanics is correct period, otherwise it will break down. So this, if we want quantum cyber, we need that quantum mechanics will work more than we know today. And I hope that it will.
It's an important event. It's the first time that Lev and I agree on something. So, but for me, I think the surprise, I believe, will come something similar to what Artur was saying. I think when we start to scale up the system, we'll include more and more and more qubits. It will become so big that maybe something interesting will come up, because there is this quantum regime, there is this classical regime, and then there is something in between. And typically when we teach you in undergrad, we say there is some kind of a smooth limit, everything goes in a nice way. Maybe there will be some surprise there.
Okay, thank you. We move to the next question. For which type of complex problems do you expect quantum computing paradigm to be superior to classical computing one?
I'm sorry, I have nothing to say about it. It's far from my field of research, so I don't have any prediction.
Well, it's very difficult to give a general answer or specific answer to this question, because the topic of the understanding the power of quantum computation is ongoing research. We have few examples where we can see this exponential separation in computational complexity, which is good. But I don't think we have a full understanding exactly what kind of specific problems it's going to be good. We can speculate. We know, for example, that quantum computers are good at evaluating certain global properties and patterns. So, for example, quantum computers will not help you to solve function evaluation in any better way. But for example, if you look at the global property of a function, say periodicity, you may ask a question, what is the period of this function? Then this is actually observable. A quantum computer can give you an answer without telling you what the values of the functions are. You don't have to know all the values to answer the question, what is the periodicity, at least in quantum domain. In classical, you have to know all the values, right? So this is one example that we know about because the whole factoring algorithm is based on this. But I think this is an interesting open question. What are other features that allow you to explore the power, and certainly global features that depend on the power of quantum interference, where you sample things from all kind of different domains and just bring them together, and you are hoping for a quantum interference on one of them. So actually, I would say it's an open question, an interesting one, but it's more like defining a research topic rather than being able to answer them fully.
I don't know what will be the problem which will be solved. From what I feel, that it's somewhat disappointing that after Scholl algorithms there is no any kind of big step, some big problem which quantum computer can solve. But I think the problem which should be mentioned at the beginning of quantum computer was David Deutsch, who really considered its parallel computation cleverly used. Because quantum computer essentially it's kind of an example of quantum mechanics as it works as many words. It's make many computation. But we cannot get all computation to know all of them. We can know only part. And the quantum computer is really take parallel computation and take some important part from every one of them to give us the right answer. I hope there will be new, important, practical result for this, but I also don't know which one.
Maybe I can make a couple of comments. Of course, it's an open problem, but comment number one is actually quantum computers can solve better problems that have certain structure. For instance, as Artur was mentioning, and Lev, the Shor algorithm, when you need to identify a period, it's a very nice structure, then it has an exponential advantage. On the other hand, when it has to look at unstructured data set, it just gives you a quadratic advantage. That's the Grover algorithm. And in between, there is probably a range of structures where quantum computer can do better, but how much better we do not know, and we need to identify that structure. Maybe the global structure of the problem, some other properties. So that's something, of course, to be researched. The second comment that I think I'd like to make is that we always think about trying to solve classical problems using the quantum computer. That's like Shor algorithms, optimizations, etc. So there I think if we will need, in order to solve the problem, to teach or introduce an exponential amount of data, that means that anyway the power will be lost. So we should not expect to solve optimization problems which are exponentially large, because just to give the data for the problem will take already exponential amount of time. So I think we should not hope there for something like that. And the third comment is that I think it could be that there will be a great advantage actually for quantum problems, and that was the original idea, I think, of Vaidman, doing it for quantum simulations, perhaps quantum chemistry, problem of this type.
Thank you. Okay. The next question for you, panelists, is what is your opinion, the main obstacle to harness the quantum world for quantum communication?
I think here Artur should be the first to answer.
Okay.
For quantum communication in particular, right? So
you can take it, you can expand it to quantum computation in general, if you like.
Well, you know, when we talk about quantum computation, there are several obstacles, of course. Some of them that are known unknowns, and there are several unknown unknowns. But the obvious one, of course, is how to screen the computer from decoherence and so on and so forth. So it's a better way of doing this in terms of quantum error correction and quantum fault tolerance. On quantum computation side, I think that it's a very interesting, because it's actually a very working in the area of quantum crypto. You see a very interesting cultural divide between hardcore conventional cryptologists who look at the cybersecurity, sort of responsible for security on a daily basis, and those who come from the quantum domain and say you know, there is this solution and this solution and this solution. So my colleagues quite often shrug their shoulders, say, oh, you know, it's just like abstract. And so there is this, I think that the two communities need to work together, but quite often I find them working against each other. So it's not about, but I think that the maturity of quantum technology is coming to the point that it cannot be ignored. So I think the hybrid system where you have both quantum communication and classical solutions are very important, including the post-quantum crypto. So I think that when it comes to quantum communication, it's not so much, well, technology, of course, is important to push it further. Having this device-independent system would be nice. But I can also see the very interesting social aspect of it, which cannot be ignored.
Maybe before you move the mic, another question following this is, what is your recommendation to the audience about post-quantum cryptography?
What is a recommendation for those?
Post-quantum cryptography then?
Well, I think that, you know, my personal view it is requires a little, as you know, there was a call from NSA to establish a standard in post-quantum. It was actually a very interesting experiment because you could see that this was open call and many of the proposed systems, well, many, at least 2 or 3, that were shortlisted were very vulnerable, not even to quantum, but to classical attacks, which was a bit embarrassing to see it actually percolating to this level. But it showed that the ability to assess the power of quantum devices is still, we still lack this power, mostly because when we construct a panel of experts, usually people come from either quantum community or conventional crypto community, and it's only, I think, the new generation that is trained in both and fluent in both will be able to make a much more reasonable assessment of this. So that's one comment. The other comment is many of those systems that we see today, lattice-based crypto systems, it's not entirely clear how secure they will be eventually. So you can see that every now and then there's another paper claiming, oh yeah, there is a good quantum attack on a lattice-based crypto. And it turns out usually not to be correct, as we saw quite recently, for example. But it just shows that you know, we are not, it's not impossible, right? So you have this gut feeling that the lattice-based actually may be doable, maybe actually vulnerable when it comes to quantum attack. So so I think that much more research is needed. And some of those standards, it's good to have standards if you want to have standards, but it may be a bit premature, I would say, to trust them.
Maybe it's just my subjective interest in quantum communication. Usually, how it was presented, we have BB84, we have Artur method for entanglement-assisted quantum key distribution. And I have 2 more difficult, conceptually different methods. One, it's really using quantum cryptography with orthogonal states, which does not rely on uncertainty relation. But maybe even more amazing quantum phenomena, today we can establish a secret key by counterfactual communication. We have Alice and Bob, we send no particles whatsoever between Alice and Bob, and we can establish secret key. This is what I consider the most amazing kind of quantum key security story. Unfortunately, for practical purposes, I don't think it has any advantages, but conceptually, the fact that we can establish secret key without any transmission of any kind of particles, I think this is what's amazing about quantum mechanics.
Yeah, so I think the problem with usual cryptography, classical or quantum, it's let's assume there is some kind of a mathematical problem which is difficult, and we base everything on that. And we don't have a proof that is difficult, by the way, not even classically, but definitely not quantum mechanically. So in my opinion, maybe no cloning could be a way out, in the sense that it does not rely on this hardness of the mathematical problem, which we don't know whether at some point somebody will find a clever solution or the computer will be strong enough, etc. So maybe that will be another way. No cloning, I think, in principle, is unbeatable.
Okay, thank you. The next question, please, is which technological platform is, in your opinion, the most promising one for quantum computation? Artur, we start with you.
I think none of us knows the answer.
This is interesting.
Even though it's a good question.
This is interesting.
I think it really depends on, as a matter of opinion. Actually, Alex gave a nice talk reviewing some of these platforms. Some of them have, like the noise, which is already below the threshold. On the other hand, the clock time is not good. So, in my opinion, there will be no one platform which is like the best one. It's not going to be like I'm #1 in tennis. One will be good for one thing, another for another type of information processing unit, and several platforms will be at the end of the day doing different things. That would be like my belief.
Okay. So we move to the next question. Do you think that fault tolerance quantum computers will be built eventually? And if yes, then when?
I believe there will be eventually, but the problem will be what kind of questions to ask the computer, and also if the computer does solve something that we can't solve now, how do we know that it did not make a mistake? So there are some real problems even if we succeed to build an ideal quantum computer. I think we are not sure yet what are the most interesting questions to ask it, and also what will be the test that we can make to make sure that it did not make a mistake if we solve something that we can't solve any other way.
A small remark about the previous question. I don't know which platform will be finally the right platform, but I should mention that there is a change in, with time. Nobody talked today about the NMR quantum computer, which was very popular, I think, even just like 10 years ago. So I think we still don't know. I also, it's not, I don't enough experimentalists to know the answer, but in general, I'm skeptical about practical quantum computer. We need first a real revolution, some new task which quantum computer can do, and we can improve it much more to solve short algorithm. What I believe, it will be very helpful that quantum cryptography needs a technology which quantum computer will provide. And it will be, I think, even cheaper and more efficient than what post-quantum cryptography, which considered with classical devices. So I'm very optimistic for cyber, for quantum mechanics. I'm less optimistic for quantum computation.
Well, it's of course, it's anyone's guess at this point. I think that we will be able to build fault-tolerant quantum devices in the future, but when is, well, probably not in my lifetime. It's not a statement about my health, but it's about...
or your age.
So it's, and I think that what is interesting though is there is, for those of you who are interested in answering this, in answer to this question, how experts in the field value or evaluate when exactly this is going to happen. There is a, I think it is Michele Mosca, and there's a Canadian company that does a poll. So they ask experts in the field and say, when is it going to be that we can build a quantum device that can actually say, RSA. And you can see that this sort of like each year, there's a spectrum from, say, 5 to 50 years from now. And experts certainly do not agree. It's very, very actually informative, so you can probably look it up. I don't know whether it's on the website, but you can find this estimate. So it clearly says that, one can say that quantum technology or quantum computers or quantum fault-tolerant technology is the technology of the future, and it will probably stay this way for foreseeable future.
In my opinion, the quantum works. Yeah, I think that every experimentalist that goes into the lab, prepares the experiment, puts an input and measures an output, is running a quantum computer. So the question will be, what's the real definition of a quantum computer that we will be happy with? But the whole universe is a quantum computer, so it already exists. I believe it will be built. The only way that it will not be built is if we discover some kind of a physical principle that does not allow it. Of course, then it will be great, even better than building a quantum computer. But otherwise, people are smart. At some point, they will overcome the technical difficulties.
Okay, so I would like very much to thank all the panelists